This is the third part of my lecture on experimental testing. Let's say something about degrees of freedom. For some probability distributions, the probability P also depends on the number of degrees of freedom in the data. And degrees of freedom, abbreviated to DF, is the number of measurements that could change at once without changing the mean. In most cases, the number of degrees of freedom is just the number of measurements n minus 1. But in general, it's the number of measurements minus the number of independent means which have been calculated from the data. Let's take an example. Suppose we've got three measurements A, B and C, and we know that they've got a mean value of 5. If we have some people A, B and C allowed to choose values for these parameters, then A and B can freely choose any number they like, but C has no choice at all. He is forced to take the value which makes the mean of A, B and C add up to 5. Likewise, if we give a free choice to A and C, then B is forced to take the particular value that makes the mean equal to 5. And if B and C choose freely, then A's hand is forced. So we say that there are only 2 degrees of freedom because only 2 of those numbers can be chosen independently. The third one is fixed because the mean has been already defined. Another thing that's important is whether we're doing difference testing or equivalence testing. What we've been talking about so far is testing for significant differences. We took the null hypothesis to assume there was no difference, and if the null hypothesis was rejected, that demonstrated that there must be a significant difference. But if the null hypothesis is not rejected, that does not demonstrate that there is no difference. It just means that we don't have enough evidence. So we can't use this method for proving that 2 things are equal. It's said that the absence of evidence is not the same thing as evidence of absence. So testing for equivalence has to be done differently. We can't just use the null hypothesis method. In particular, differences may be statistically significant but not scientifically or clinically important. So we need to define how big a difference matters if we're going to do any equivalence testing. Let's just have a quick look at that. This graph shows the difference between 2 measurements, and the region about 0 is not clinically relevant. It's close enough to 0 to not matter. So we could get a result here. The width of the yellow error bar shows the mean where the circle is, and the ends of the error bar show the 95% confidence limits. So if we get a result like this, the mean value is within the not clinically relevant area and the error bar crosses 0. So statistically it's not significant because it includes 0 within the 95% confidence limits, and it's also not clinically relevant because it's entirely within the range that we would consider to be unimportant clinically. Here equally is a result that is not clinically relevant because it's entirely within the shaded area, but it doesn't encompass 0, so it is statistically significantly different from 0. So we have a result that is statistically significant, but that doesn't mean it's clinically relevant. Here is a result which is statistically significant, but it doesn't include 0 within its 95% confidence limits, and it's also clinically irrelevant. It's outside the area that we would deem to be not relevant. But here is a result that is not statistically significant because it does include 0 in its range, but we can't say whether or not it's clinically relevant because the error bars are too great. Here, though, is a result that is statistically significant because it doesn't include 0 in its range, but we still can't say whether it's clinically relevant or not because it's partly in and partly out of the range. So that just shows that statistical significance and clinical relevance are 2 different things, and equivalence testing is not going to be included within these lectures, so I'm not attempting to cover that. But what we are covering in these lectures is inferential statistics. Inferential statistics are tests that will infer something about the population based on a sample. We said quite a bit about sampling and how we can try to make inferences from it. And the remaining lectures will cover several tests to compare means, tests to compare standard deviations, and tests for correlation and regression. These are all examples of inferential statistics. In particular, we'll be applying the methods of hypothesis testing that we've been talking about in this lecture, and each test will generate its own test statistic and will have to be tested against the appropriate probability distribution. So we will apply the methods of hypothesis testing that we've been looking at in quite a few different circumstances. In particular, we'll be looking at parametric and non-parametric tests. Parametric tests are those based on estimates of some parameter or number that represents an underlying distribution. The requirements for that are that the data must be quantitative. We must have a number where we can calculate a mean in order to look at the distribution. And for most tests, it's important that the data should be approximately normally distributed. It doesn't have to be a perfect normal distribution, but most tests do assume that it is roughly normally distributed. In other words, it is reasonably symmetric and the tails aren't too large. Alternatively, we can use non-parametric tests that do not assume any particular underlying distribution. So we don't need a parameter to parameterize the distribution. There are no particular requirements, in fact. It will work with any sort of data. It can be quantitative or categorical. It will work with quantitative data even if it's not normally distributed. So non-parametric tests are much more general than parametric tests. However, parametric tests have a greater power, so if possible we should use parametric tests rather than non-parametric tests. But in the following lectures I will try to include examples of both. So what we've learned in this lecture is that researchers control the independent variable and then take measurements of the dependent variable. Data can be categorical, which is nominal, which is names only, or ordinal, which are names that can be arranged in order, or it can be quantitative, which is numbers. And we get results which are tested against the null hypothesis. And then we use the appropriate statistical tests, which we'll describe in future lectures, and they may be parametric or non-parametric tests. And we obtain a test statistic which we compare against the appropriate probability distribution using the appropriate number of degrees of freedom, and then interpret the significance of that probability. A probability greater than 0.05, the result is not significant, and a probability of less than 0.05 gives a significant result. So we'll be applying these techniques many times in the coming lectures. So that's the end of this lecture on experimental testing.